Hi, everybody. Welcome back to the Feynman technique. Today, I have got a really good integral for you. We will be using Feynman integration in combination with complex numbers to solve this. All right. So, what are we going to do for our first step here? We're going to define a parameterized function, and it's going to be equal to this right here. That is, f of t is equal to the integral from negative infinity to infinity of this new integrand here. And you'll see I chose that parameterization because that way, when we differentiate with respect to t, you'll see we'll recover this factor of x right here. All right. So next, we're going to complete the square. Let's complete the square on this right here. We can rewrite that as by rearranging and factoring out a t plus 1, we can get it to equal this. And then next, we can rewrite it like this. Just bring that negative sign out and then complete the square. All right. So what does this mean? This means that we can rewrite our f of t like this. Go ahead and pause the video and follow along with those steps if you'd like. But this is our new f of t. All right, what next? Let's just evaluate this integral right here using the substitution u is equal to x minus t plus 1 over 2. The limits of integration are not going to change when you do that. So this integral right here just becomes this. All we have is this, and this is very well known. That's the full Gaussian integral, and it evaluates the square root of pi. So f of t is just going to be square root of pi times e to the quantity t plus 1 squared over 4. All right. So next, we're going to differentiate our f of t with respect to t. We'll differentiate this one first. And with respect to t, if you do that, we will get this right here. Again, the steps are laid out right here. This is what you get for f prime of t. Now, alternatively, we could have used the Leibniz rule for differentiation under the integral sign to arrive at f of t, f prime of t being equal to this. All we do is pass the derivative inside the integral sign and then take the partial with respect to t of the integrand. So we have two different ways to differentiate f of t. One of them gives us f prime of t is equal to this, and the other gives us f prime of t is equal to this. Therefore, they are the same thing. So we have this. We have that this integral simply evaluates to this. All right. Well, how does that help us? Now's the time to introduce complex numbers. Notice that cosine x is just the real part of e to the ix. So we can rewrite our original integral as simply the real part of this part right here, of the integral of this part right here, times e to the ix, which can be rewritten like this. All right, and this is exactly our original f of t evaluated at t is equal to I. So we can say that f prime evaluated at I is equal to this, which is in turn equal to our other representation of f of t evaluated at t is equal to I. So now we have this equality right here. All right. So now we can compute the final expression right now. First, let's just see that I plus 1 squared is going to evaluate 2i. Therefore, I plus 1 squared over 4 is just I over 2. But we have e to the I over 2. Well, that's just cosine 1/2 plus I sine 1/2 by Euler's formula. So now we are done. We have f prime at I is equal to, again, it's going to be this thing evaluated at I. and then we need to take the real part. So what we get when we take the real part, if we expand this out, taking the real part of this is just going to be square root of pi over 2 times the expressions that will be real. That would be this 1 times cosine 1/2, and also this I times I sine 1/2, which would make it negative sine 1/2. So the real part of f prime at I is equal to this, and don't forget our I was the real part of our f prime evaluated at I. So our original integral evaluates the square root of pi over 2 times the quantity cosine 1/2 minus sine 1/2. So this integral all the way up at the top right here evaluates to square root of pi over 2 times quantity cosine 1/2 minus sine 1/2. All right, guys, I hope you enjoyed that, and we will see you next time.